one of the smallest gardens, working on the smallest plants, drinking the tent juice. What?
Dancing up, bouger, dancing up, see me dancing up, bouger, dancing up, to the left, dancing up, to the right, dancing up, see my money dancing up, yeah, dance, ay, 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 aqua, ba, 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 ay, 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 aqua, ba, 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 see me dancing up, see me dancing.
Hey, this is the beautiful garden of Talca, Chile. We're surrounded by beautiful trees and plants. Hey,
This flower presents this magic garden. We have a lot of seeds and we planted deep processing.
developmentally genetics.
Source from Me.
I'm Vladimir,
And I am Aygün.
and we're at the Road Center for Human Neuroimaging in London.
Hello, this is the Hubert Garden of CuttingGardens 2023 conference.
I did move, I did dance, then they look and they pass. If I bought spots, they go wrong. Play music, then go dance. I did move, I did dance, then they vex. Give me
Hello, this is Havana Garden over here. Thank you very much for inviting us to this multi-hub scientific meeting. Thank you to the MEEG Association and to the organizers for inviting us.
See me dancing now, see me dancing now, see me dancing now. Go better, see me dancing, dance, ay ay ay. See me dance, dance.
Hello from Downlane Garden.
Where I come from, see me them a dancing now.
Hello, everybody. Fourth and last day here at CuttingGardens. First, wanted to thank you all so much for sending these very nice videos. It's really cool to see all faces. Yeah, it's a great pleasure to chair this last session on deep neural network analysis of MEEG data. So we're going to hear three speakers today: Hubert Banville, Maarten De Vos, and Radoslaw Cichy. Sorry if I mispronounce your first name and last names as well. So let me first introduce you to Hubert. Hubert, salut, where are you? Yes, he's here, he's coming. And are you pushing him on stage? Yes, thank you guys. Okay, hi Hubert. So Hubert is currently a research scientist at Meta AI. He's completed his PhD at the Université Paris-Saclay. His work focuses on machine learning for the decoding and processing of neuroimaging data. Hubert, if you want to start your slides, the floor is yours.
Perfect, thank you. All right, well, thank you for the introduction. Thank you very much to the organizers for inviting me to this session, and to the Bournemouth Garden for welcoming me here today. So in my talk, I want to tell you about how we can go beyond pure supervision, full supervision, when using deep learning or representation learning with MEG and EEG. So it's not going to be a long presentation, but I wanted to cover quite a lot of ground. So I'll start by giving you a short introduction to deep learning in general, and then for MEG and EEG, for the people in the audience who might not be that familiar with the core concepts of deep learning. And then I'll share two examples of how we can go beyond full supervision. First of all, using self-supervision, so a type of unsupervised learning that will apply to some pretext and downstream tasks. And in a second part, I want to tell you about some new, quite exciting results about how we can use contrastive learning and generative image modeling to decode visual stimulus in a time-resolved manner. All right, so starting with a short introduction to deep learning. So I assume that a lot of people in the audience might be familiar with a more traditional or feature-based approach to machine learning. And so I'll ground my introduction with this comparison. So in both cases, we typically start with some EEG data or MEG data. We'll typically want to work with a smaller chunk of data, so we might extract a kind of window around it. In both cases, we'll want to start with pre-processing steps. And so in a traditional machine learning setting, that's very important. You want to apply temporal filtering, spatial filtering, maybe doing some artifact correction. We also do pre-processing in deep learning, though we'd like this step to be maybe less involved and to let the deep learning architecture take care of most of it. Then a critical point of a traditional machine learning approach is feature extraction. So in this stage, we want to extract maybe as many features or features that you know will be relevant for the task at hand, and that will help your statistical model to classify or regress the target of interest. So here I listed a few examples, but this is really up to the developer of this machine learning pipeline to decide which one makes sense for the task. On the other hand, when working with deep learning, we don't think so much about the features themselves. We instead spend time thinking about the architecture. So what kind of neural network you'll use for this, for solving this task. And then in both cases, you end up training a model with potentially similar or dissimilar optimization approaches. So one main advantage of a traditional machine learning approach is that it's interpretable, because since you've extracted the features yourself, you know what they represent, and then you can look at your trained model and see the importance of each feature to both get a deeper understanding of what's going on in your data, but also for doing some sanity checking and making sure that your pipeline works as intended. Though this comes at the expense of having to do an extensive engineering effort, because you have to think about these features and potentially compute them. On the other hand, when doing deep learning, we spend probably as much, if not more time, thinking about what kind of neural network architecture we want to use, and also what kind of training hyperparameters we need to use. And the advantage, though, is that we can potentially discover more optimal features or better features than those that we could have implemented ourselves. All right, so kind of going to the three main components you have to think about when designing a deep learning pipeline. So first, I already mentioned the architecture. This specifies the space of functions that can be modeled by your neural network. A classic example would be a feed-forward neural network or a multi-layer perceptron. Here we have a two hidden layer multi-layer perceptron. But there's a plethora of different layers that you can think about and decide to use, such as convolutional, recurrent, attention, graph layers, etc. Second component is the loss function. That tells your neural network what task it's performing and also how well it's performing it. This will really depend on what kind of task you're trying to achieve. So if you're doing multi-class classification, you'll typically use a cross-entropy loss. If you're doing regression, maybe a mean squared error loss, clip loss for retrieval, etc. And then finally, you need a learning rule that will tell you how to change the parameters of your model based on how it's doing on your loss function. And luckily, with deep learning, it's typically some kind of flavor, stochastic gradient descent, along with backpropagation that we use. All right, so this was a very, very high level overview of the main components that you have to think about when doing deep learning. Now, how has this been used in practice in EEG and MEG? So to answer this question, I wanted to show you some results from a systematic literature review that we did in 2019, looking at 154 studies using deep learning for the analysis of EEG. And then we read all of these papers and extracted key information and tried to summarize it in the review. So first interesting result in that is that between 2010 and actually July of 2018, we saw a big increase in the number of papers interested in applying deep learning to EEG. Before 2015, we had fewer than 10 studies, and that reached more than 60 in 2018. The second thing I want to highlight here is that this was used across the board in many application domains of EEG. So we see here examples in brain-computer interfacing, epilepsy, and sleep, among others. So now this was in 2019. What has happened since then? So I ran a similar query on Scopus 2 days ago because I was curious. And kind of expectedly, we see that this trend has continued. And if we look in 2022, we have probably at least an order of magnitude more papers that were published on this topic. My guess is that this will continue to grow as deep learning is now kind of the industry standard for many machine learning heavy tasks, such as natural language processing and computer vision. And what about MEG? Well, the numbers are much lower, but we see the same kind of trend over the last few years. All right, well, going back to one of the main components, architecture, what have people been using for EEG? Well, what we saw is that up until 2018, people were mostly using variations over convolutional neural networks, recurrent neural networks, or maybe combinations of both. In terms of depth, so that is how many layers you add to your neural network, we saw that actually most studies reported using only 2 or 3 layers. So that's not that deep, actually, compared to some neural networks that are using computer vision, for instance, that can be hundreds of layers deep. One other important point that we highlight in the review is the dimension of data. What kind of data sets are available and are used in these studies to train the deep learning models? What we saw is that the distribution of the number of examples varies quite a lot between the different subfields of applications, different application subfields of EEG. I think the median here was around 14,000 examples, which is not that much when we think about the fact that in computer vision, for instance, this classic ImageNet dataset that's been around for more than 10 years contained 1.3 million training examples. We can reach in some studies, especially with sleep, it seems, this kind of sample size, but it's still quite rare in the field. There's many more results and insights you can find in this literature review. One thing that we try to do is also a little meta-analysis of the reported improvement in performance between traditional models and deep learning models. But I won't share too much about that because I believe that Maarten's talk will be on this topic. All right, so this was a very short introduction to how deep learning can be used with EEG and MEG. Now in the second part, I want to show you how we can go beyond a fully supervised classification or regression task by using deep learning and specifically something called self-supervision. And let me introduce self-supervision with an example coming from our paper in Journal of Neural Engineering. So let's say you're given some EEG or MEG recording, but it's unlabeled. You don't know what happened in there. How can you make use of this data? Well, one approach is to randomly sample windows from that recording. So I don't tell you where I sample these windows from, but they are from somewhere in that original recording. Now the question we want to ask, and I'll ask it to you first, is are the windows close to each other or are they far apart? And I'll remove the original recording. All right, so take a second to think about it. Ultimately, we don't want to do it ourselves. We want to use this as a pretext to train our neural network. And so that's what we're going to do. We'll design a feature extractor, H-theta here, that will apply to both windows. And then we'll feed the output of these two models to a contrastive module, essentially another tiny neural network, whose goal will be to predict whether or not the two windows are close or far away in time. So why is that useful? Why is that important? Well, if you thought about it yourself, you might have realized that low frequencies might be a good way of deciding if the two windows are close or not, or maybe looking at high frequencies, right? And so by training your model with this approach, you actually force your neural network to encode and discover some structure about the raw data, which means that you can then reuse this as a feature extractor or an initialization of your weights. So if you're curious, that's where the two windows came from. So this is an example of a self-supervised pretext task. And there are other ways of doing this. For the sake of time, I won't cover this one, but there are many different ways of defining pretext tasks. So once you've pre-trained your network, you can freeze its weights and reuse it as a feature extractor. And so let's say you're interested in a downstream task like sleep staging. Well, what you might do now, given some labeled data, you might take a labeled window from your recording, feed it into your pre-trained neural network, and then use its representation as a feature vector to further train maybe a shallow classifier to predict what sleep stage that window is from. Does this help in practice? Well, what we showed in our paper is that in a certain data regime, that is when you have few labeled examples in your downstream task, sleep staging here, you can actually improve the performance of your model quite a lot by pre-training it first. That's up to a point though, because if you have enough labeled examples, then maybe a pure supervision approach will give you as good or maybe better results. Interestingly, you can also inspect the feature space that was learned by these networks, both as a way to discover patterns in the data. Here, what we saw is that just with this unlabeled pretext task, we could learn about the macro and microstructure of sleep. All right, and if you're interested in similar approaches, I cited a few papers here that used the same concept and also tested in most cases on a sleep staging downstream task. All right, and for this last part, I wanted to give you a glimpse at a paper that was actually shared yesterday, so it's still quite new. If you want to take a look at the blog post, I put the link down there. And so this part will be on using contrastive learning and generative image decoding, generative image modeling as a way to do visual decoding in a time-resolved manner. So in the case of image decoding, we're interested in the following problem. We have someone looking at images. We collect some of their brain activity, MEEG in this case, and then we'd like to feed that brain activity to a neural network such that we can regenerate the input image pixel by pixel. So ideally, we'd like to do something like this in an end-to-end manner, such that we have a single neural network that can output a new image. The problem, though, is that the space of natural images is really, really large, and it might not be the best approach to just train this whole thing end-to-end. Actually, what we'd like to do is reuse some building blocks from the computer vision literature, where we can already generate natural images pretty well. And that's what I'm going to tell you next. So I'm going to go block by block, telling you about the different components of this approach that has mainly been used so far with fMRI data. But here we focus on MEEG, and we use this data set called Things MEEG that was published quite recently, where people, where actually 4 participants were sat in an MEEG device and looked at more than 22,000 unique images of things, animals, objects in a rapid serial visual presentation where each image was presented for 500 milliseconds, followed by about a second of a gray screen with a fixation cross. Okay, so we have this data. Now what we want to do is apply 2 models, one image model and one brain model. The image model here is something that, again, we took straight from the computer vision library. And these models were all pre-trained to get to some kind of feature representation of images that captures the main, the important information in the images. I listed them here, but I won't go into details right now. On the brain side of things, we also have a deep learning model. Here we use a dilated residual convnet from a paper from our team, adding on top of it a temporal aggregation layer and output heads for the different parts of our loss. So the goal here of the brain model is, given the MEG data, produce as similar representation as possible as the representation of the corresponding image. And the way to do that is by using a dual loss of retrieval and reconstruction. For retrieval, we use what we call the clip loss, which was originally designed for learning to match text and images. In our case, we don't have text, we have brain data, and we don't have a text encoder, we have our brain model. And on the reconstruction side of things, we have a standard mean squared error loss. We then combine these two with a convex combination. Okay, so with this step, we can hopefully align the representations of the image model and of the brain model, which means that we can now feed the output of the brain model, given some new MEG data, to a generation model. This is a model that is trained to generate new images, given some conditioning information. And here we follow the approach of Oselik and Van Rulen, published in Scientific Reports recently, where we feed 3 types of latents to this generation model, which will then hopefully generate brand new images. All right, let's get to some results. So a first step, maybe an easier task, easier question, is to ask, can we retrieve similar images to an image someone has seen, just based on the MEG response to that image? The answer is that yes, in most cases, but it depends on the type of image representation that you use. So if you use something like Clip Vision, Dino V2, VGG19, you can actually reach quite high top 5 accuracies. So that's a retrieval performance of about 70% here. What does this mean in practice? Well, if you show these images to your subjects using this approach, and depending on which latent representation you use, we can recover images that are actually quite similar, both in terms of semantics and sometimes in terms of low-level details. What's nice about MEG, though, is that we have quite a high temporal resolution as compared to fMRI. And so we can also think about an expansion of this analysis, but in a time-resolved manner. So we repeated the same analysis, but now instead of taking the full 2 seconds around the presentation of the image, we use smaller 250 millisecond windows and repeat this analysis for each window. And so what we see is that before the presentation of the image, performance in retrieval is actually at chance level. But then a few tens of milliseconds after you show the stimulus, you start getting much higher retrieval performance. And this decays slowly after the presentation of the image, going back to chance level a second and a half after. And again, we can look at, in practice, what this looks like. So before the presentation of the image, we have quite random or at least unrelated images. And after the image is presented, we start, especially if you look at the 3 first rows, we start getting retrievals that are actually related to the true image in the first column. All right, can we go beyond retrieval and actually generate these images next? Well, the answer is yes, mostly. If you see here, so first row is always the seen image, second row is the generated image. And then we divided this into 3 categories, so best generation, average generations, and worst generations. This is done based on some image quality metrics that are widely used in the field. And what we see is that for the best images, we can sometimes recover the semantics, for example, animals, let's say people or food, and sometimes also low-level details like maybe the orientation, the pose of the animals, etc. In some cases, though, and especially for the worst one, we see a lot of failure cases. That could be for many different reasons, but this means that it doesn't work in all cases. And finally, final result here, we can also repeat this analysis, but in a dynamic fashion. And so here it's a slightly different approach where we start with a 100 millisecond window, try to decode from that, and then gradually add more and more data until we cover the entire interstimulus interval. And what we see is that at the beginning, the image might be a bit more random, but as you add more signal, the generation becomes better and better. All right. So that was maybe a lot of stuff. So I want to summarize a little bit. So I hope I convinced you that deep learning has become an essential component in the MEG-EEG analysis toolbox. And as we add more and more data sets and larger data sets, this will increasingly become the case. I showed you two ways we can go beyond a purely supervised classification or regression approach. First, using self-supervision to make use of unlabeled data to improve performance on downstream tasks. And then using contrastive learning to interface with generative image pipelines for visual decoding. And so to me, some future steps and perspectives that are particularly interesting are this idea of trying to find the best architecture for dealing with MEG and EEG. I think there's been a lot of effort in the field so far in this, but we can probably get inspiration from other fields of applications of machine learning and improve on that. In terms of self-supervised learning, we're still looking for what is the optimal configuration of pretext tasks given the downstream tasks that you want to work on. And finally, something that we highlighted in our initial literature review that I told you about is the importance of open research, code and data sharing that I think the field is actually moving forward towards in a very nice fashion. And well, with this, thank you everyone for your attention. I listed here some toolboxes or tutorials you might be interested in if you want to try deep learning on MEG and EEG. Thank you.
Thank you, Hubert. This is an impressive talk. Quite excited to read the questions that everybody is going to write in the Q&A right now. We will take our usual 7 minutes break and we'll see you then. Okay, first question. Can we use these methods on mental imagery tasks? Not with seen images, but imagined ones.
Yeah, thank you to the Bournemouth Garden for this one. So yes, what we've seen in the literature is that going to mental imagery is definitely harder than going with kind of perceived stimulus. That's the case already with motor imagery, BCIs, right, where motor execution can actually lead to better performance than motor imagery. It's the same thing with other imagery tasks, though I'm not aware of a specific paper reference for this. One thing I'd say, which kind of like follow up to this question that we got here, is could we do this on dreams? Well, there's actually some research, I think, which was done on fMRI, trying to decode visual processing during sleep, during dreams. So that might happen.
This is getting scary, though. Okay, thank you. All right, can you train these networks instead of time windows with some specific signals, like an ARP, to find neural signatures of some task or yeah?
Yeah, definitely. I think that's the great thing with these pretext tasks. They're really flexible. So if you're working with time-locked windows, locked to a stimulus, you could still apply a very similar approach, where it's just that instead of sampling from anywhere in your recording, you sample from these stimulus presentations, so windows around these stimulus presentations. I don't have specific results on this, but I believe it should work as well.
Okay, nice. And in the same vein, can you train a model? Do you need to train your model on each subject? You use 20,000 images, I believe, or is it possible to generalize across subjects? So something about inter-subject generalization.
Yeah, that's a good question. Actually, if you look at the fMRI image generation literature, most models, if not all, I think so far are subject-specific models. That's potentially because of the specificities of the fMRI signal. You might not end up with the same number of voxels per subject. In this case here, since we had our neural network architecture that could already work and generalize across subjects, we were able to train our models on all 4 subjects at once. But you could definitely also train subject-specific models if you'd like. Oh.
Really nice, thank you. Okay, for a reliable generation of images from MEG, how large does the training set have to be? Any estimates?
Yeah, good question. We haven't looked into that specifically. My assumption is that it would also depend on the number of categories, of types of images that you want to be able to generate. But yeah, I'd say this is an empirical question, and I sadly don't have the results.
Okay, thank you. Can you use this deep learning, machine learning methods to generate EEG or MEG data for population that we cannot access as easily, for example, patients?
Yes, definitely. Actually, even in 2019, when we did the review, we saw that there were 2 or 3 papers that looked specifically at the generation of EEG, potentially also MEG data. And yes, that's something that you could use it for. So if you do have access to a few recordings of people from a patient population, for instance, you could train your generative model to generate EEG or MEG data and potentially augment your data set with these artificial examples. One thing that I would also mention here is self-supervised learning might be helpful in this case too, because maybe you don't have a lot of labeled patient data, but maybe you do have a lot of patient data. And so if you can pre-train your neural network with this unlabeled patient data, you might be able to bias, in a sense, your neural network to represent data from these populations before fine-tuning your network on a smaller set of labeled examples.
Amazing. Okay, did you try to assess to what degree image-specific micro eye movement behavior, which propagates to the EEG MEG signal, contributed to the decoding performance or the modeling results?
Good question. We haven't specifically looked at that. We truly had an end-to-end deep learning approach where the only preprocessing that we did was, I think in this case, actually, we didn't do any temporal filtering. We only did baseline normalization. So we can expect some artifacts to remain in the data. We haven't looked specifically at their impact on the, I believe, yeah, this is image specific. We haven't looked at the impact on image generation. However, what I'd say is we have a very large set of test examples that covers many different categories with different examples per category. So there's quite a lot of variability in the images themselves. So it might be hard to find a specific effect of kind of artifacts on a type of image.
Thank you. Yeah, move on. Is most of the information in the spatial aspect of the MEG or in the temporal aspect? If you scramble the time samples, how much will it degrade the performance?
Mm-hmm. Yeah, this is a good question. I think it also relates to the priors that you use when you design your neural network. in our case, for the last part on MEG, the neural network that we used is essentially a sequence of convolutional blocks with convolution across both the spatial dimension and temporal dimensions. So both of these aspects are important for a neural network. Definitely what we saw is that the spatial aspect is definitely important to take into account when dealing with multiple subjects. So training one model in multiple subjects. So because of this idea of having temporal convolutions, shuffling the data in the temporal dimension would break the structure, and so you'd lose a lot of performance. Definitely.
Yeah, thanks. Okay, I assume you feed the raw data into your deep learning models. Since you skip the feature extraction step, do you then assume that the extraction layers are going to decompose the signal or in some way extract some useful information to perform the classification? Would it make sense to rather feed some pre-processed data with some features already extracted? So, in other words, how much do you think that the pre-processing of the data still matters? Because I guess you assume that the first layers are going to do that for you, but how do you then get access to this information? And I guess that's another question. Well, good luck.
Well, I think this ties in a little bit with the previous question, which is kind of the priors that you use when defining your neural network. You're right. In this case, we didn't use a lot of pre-processing. So I mentioned baseline normalization. That kind of takes care of the big DC offsets. And also a scaling. So using the statistics of the entire training set, we just scale each channel such that it's centered around the median of the distribution, and then its spread is also normalized somehow. An important step which I didn't play with, but I know was critical in the previous speech decoding work of my team, is actually clamping the values. So some channels are so noisy that the values will go way above the standard deviation or interquartile range of the distribution. So applying some kind of clamping on this really helped. So that's one example of pre-processing choice. So
that's like removing big artifacts, right?
Yeah, essentially.
Yeah. Okay.
Flatlining channels when they are too large. Yes. So this is it for pre-processing. And so what we expect is indeed the first layers to actually learn spatial filters. That's how our architecture is set up. And then the convolutional blocks that follow to learn more about the temporal structure. And so they're not explicitly, they're not kind of a standard convolutional kernels, dense kernels. They're actually dilated. So the interpretation might be slightly different. Dilated convolutional layers, in this case, just means that your kernel is applied to one input unit every few input units. So you might have one weight, then nothing, another weight, nothing, another weight. So this allows you to have a larger receptive field for your model. So the parallel with temporal filters might not be as straightforward as standard convolutional layers, but I'm sure there's still a way of interpreting these kernels as doing some kind of temporal filtering.
Okay, great. Do I have more questions here? One more. What can we learn about the brain from this generative AI work? Good luck again.
Yeah, well, actually, I think this is an interesting segue to Radoslav's talk, I believe. I know that his work centers around how to use neural networks not only to process EEG and MEG, but also as a way to model the visual processing stream. So maybe that's a question we should keep for him.
Okay, we'll ask him then later. Okay. Before closing, I want to ask you another one about the interpretability of those hidden layers. Actually, are there people? I guess there are people looking into these layers and trying to interpret like what those patterns mean. Do they represent anything that makes sense? I guess that's also something that we're going to talk about with Radek later on. But so in your field, how does it look?
Mm-hmm. Already in the literature review, we pointed out that some people had started trying to interpret the weights or also the activations of the neural network. So there are different ways of doing it. There's definitely some interesting results that you can get to kind of recover either information about where in the head, let's say, which channels are the most important. That can kind of be a good sanity check if you're doing, say, motor imagery, right? You know which channels should be most useful, but you can also do the same in the temporal domain, and you can combine both domains. I believe it's still a very active field of research in machine learning and deep learning in general, interpretability, and trying to figure out what has the model learned, what does it represent. And so I'd say still very much an open question for EEG and EMG, but if you're for anyone interested in this, there are already some approaches that have been proposed.
A final one. What does Meta AI project as like potential utilization of this work? Can you give us a little insight?
So all I can say about this is I'm part of FAIR, which is the Artificial Intelligence Research Lab, and we work very much like an academic lab. So all of our research is published and peer-reviewed, and we publish our code, data, models, if possible. So we work very much like an academic lab on that level, and we focus on scientific questions. So yeah, this is it.
Okay. Thank you very much, Hubert.
My pleasure.
And yeah, I guess everybody is ready now for the next talk.
Yes. Thank you very much for the invitation, and also special thanks for Hubert for the introduction. What is deep learning? So I can skip some of the slides there. We're just fitting the camera now. Okay, great. So Hubert hinted already about, okay, there's an increasing number of papers, so probably there is something about deep learning that beats machine learning, but is it just performance? That's the question that I would like to address a bit in my talk. So recapping a bit, in AI, artificial intelligence, which is currently used in the real world in medicine and also in the EEG research, it's about learning from data. So we're trying to say we have a lot of data. We also have a lot of labels, and we try to find the relation between this data and the labels. We do this by looking at what we call training data, so where we all optimize the parameters. And the proof is actually, does the model work on unseen test data? And because we don't know what is the real unseen data, we typically take a part of our data and use it as test data. But the real value is really, if I give you data that you've never used, does your AI still work? And this is a different way of saying what Hubert said, like, if we have to address these questions, and it can be anything. It can be a BCI where you try to discriminate left and right motor imagery. It can be a diagnosis. Are you healthy, or do you have, in this case, Parkinson, or so on and so forth. We try to use machine learning to answer this question. And machine learning is nothing else, if I can say, as defining in the classical way some features and learning a simple model, or in deep learning, learning a more complex model that learns both the features and the decision boundary in the same time. And so this is what Hubert referred to as we are having more and more deep layers, because we can increase the number of parameters, and increasing the number of parameters in your model increases the complexity. It's new, but in the same time, this was the Mark I perceptron from the 70s. And so it looks much like a deep learning already back then. The only difference now is that we have more data, more compute power, and also a slightly better algorithms to really solve the problems. So introducing the question on performance, like quite some years ago, we thought, okay, there is deep learning. ECG has a lot of labeled databases. Is deep learning better than feature approaches? And I copy here the abstract, and if you would read it in detail, you'll see that we want deep learning to be better, but in fact, it performs on the same level as the good old classical machine learning. Also credits to Tonio Ball, who introduced like convolutional neural networks for EEG. He was fan of deep learning in the early days. He published on it. He said, like, look, I can classify healthy EEG from pathologic EEG with good accuracy and with simple models. But then he was also very critical and said, like, my new deep learning models are better than the traditional classical machine learning. So he did a lot of effort optimizing the classical machine learning models. And again, he's found, like, actually, probably we have similar accuracy, kind of suggesting the value is really in the data and maybe less in the model if you make a good model building. But okay, this is not the end of the story. We're interested in sleep, and in particular, for example, as a motivational example, REM behavioral disorder. If you're not familiar with it, sleep has different stages. You have light sleep, deep sleep, and you have a special sleep, REM, rapid eye movement sleep, and it's associated with dreaming. One of the disorders, REM behavioral disorders, is when you're dreaming, your brain is active and your body is paralyzed, or like there is no muscle activity. In REM behavioral disorder, this is not the case. You start making violent movement, you can be screaming and so on, and it's a precursor of Parkinson. So that's why we're interested in it. Can we detect it in an automated way and ultimately screen the whole population? So for this, we do a sleep recording. We apply EEG and some EOG or EMG activity. And in the picture, you see the difference during REM in EMG signal between the healthy person, where there is no movement, and the unhealthy person, where there's a lot of muscle activity. And as we started, so we had to detect REM stages and then quantify the activity. And in order to do this, we started from a classical machine learning approach. And we did a REM screening with relative good accuracy. So it worked pretty well. And if I show you some of the results and how well we do the sleep staging, you can visually appreciate that even in a disease population, the estimated hypnogram matches pretty well the ground truth hypnogram that was annotated by the human. Still all feature-based. So why deep learning then? Actually, if you think what we do in sleep staging is we take 30 seconds of the EEG and give it a label. But you know that sleep stages don't change every 30 seconds. If you're now in light sleep, the chance that you will be in light sleep in the next 30 seconds is pretty high. And so this you can use to predict, okay, what is the sleep stage of your neighboring epochs? But also, in the opposite way, you can use the information of the neighboring epochs in order to infer what is the label of your current epoch. And that's also what visual human scorers will do. They will go back and forth between the EEG pages of 30 seconds in order to give this label. And actually, deep learning has a very elegant way of building such what we call sequence-to-sequence models. So we take multiple inputs at the same time, and we try to predict multiple 30-second epochs at the same time. So you can do this in a traditional feature-based approach, but it's pretty elegant in a deep learning-based way. And so this was one of the first networks that we built. We called it SexSleepNet. And it might look complicated, but it has only 2 layers, where basically we kind of look at the information within the 30-second epochs and have a second layer on top of it, where we look at the information across multiple epochs. And we found that like 20 epochs of 30 seconds was a pretty good way of integrating the information across time. So from this, we can estimate the sleep stages. And then if you look in like a fairly honest way, if you looked at the literature, you would find like low 80 performance with feature-based. And suddenly we had a jump of, let's say, 5% in accuracy. So there is value in using such models in order to improve classification and sleep staging. Obviously, we trained a lot of data. I'm not going into all the details. So this was our first model. Then we thought, okay, maybe we can do better. We can use all kinds of tricks from the AI community, from the deep learning community. And we can, for example, integrate raw EEG and spectrograms in the same way. We can use transformers. Maybe you've heard about it. They're also kind of the basis of speech models, language models, and so on and so forth. And what you see is that actually, if you look at our first model, SexSleepNet, we had like something in this order of magnitude on a certain database. And then we creep up performance marginally. We're always doing a bit better, but does it really matter? I don't think so. You know, it's not having any real impact in terms of applications. But what we can do, for example, is sleep monitoring in real life. Again, so what I showed you previously is that we have data from a sleep laboratory where there's a lot of data. We have EEG data and this EOG. We have a lot of EEG channels. In our models, we always used only one channel. But we can also think about more convenient ways of recording brain activities, like channels behind the ear or EEG electrodes that we printed on electrodes, which fit nicely around the ear. But this gives us low channel EEG information, a bit of different information, and the question is, can we still derive the sleep staging from this? So this is the postdoc in the lab that worked on it. He's now in Aarhus. And we fitted like 10, 11 subjects with this device. And we looked again, can we classify sleep stages from such recordings? And the answer is, if you automatically stage PSG and you automatically stage the data from the cigarette, performance is very similar. Again, we started off with classical machine learning. Define the features, train a random forest, and show the performance. For us, it's interesting because if we gave the new data to the manual experts, they were not able to classify. Why is this? Normally, we look at C3, C4 on top of the head. This time, we look at channels around the ear, which look different, and you see also the channels are close to each other, so the amplitudes change quite a bit. It is nice because our automated model beats the human, which is typically very hard in classification performance because the human is your standard. I mentioned, okay, this is still feature-based. We always start with features because it's kind of giving us a baseline. We also had only 10 subjects, so there's different data. It's maybe a bit harder to use like deep learning. But then the same postdoc, when he got his faculty position in Aarhus, there he was working on in-ear EEG, so placing electrodes inside the ear canal to measure sleep. And he said, like, why can I not use your sex sleep model in order to train the model on the data from all my subjects? He trained it, no fiddling, no fine-tuning. Within in a week or so of training, he had the results, and they were pretty good. They were like, okay, I can use this. And if you look here at the errors, you see that actually most of the errors in the final result were just at the transitions. So you maybe transition from stage 2 to stage 3, one epoch earlier or later, which is probably not so important for the human. So a lot of this good model confirming, like, again, the value of just using those deep learning models out of the box. And actually, if maybe you've seen this is NextSense coming out of Google X, which also give kind of in-ear EEG recordings. They also ask us, like, can we use your model? We give the model, they fine-tune it a bit, and it works out of the box. So again, showing like this, once you have a robust model, training it is actually, or using it, deploying it, is actually fairly good. Obviously, we can always keep pushing the model. We think, can we make new models? This is actually a model which we call L6SleepNet, long SexSleepNet, where we actually try to integrate like data across 90 epochs. Why 90 epochs? That's probably around the duration of a full sleep cycle. So we thought, like, if we can look like the human, we cycle through the different sleep cycles, maybe we might integrate it, integrate and extract more information. The reason we didn't do it in the beginning is because it's computationally quite expensive to track it and to optimize all the parameters. But then we found some tricks which are discussed in the paper. And if you look at the results, in green we have the results of the long SexSleepNet, and in red we have the results of the original SexSleepNet. And again, like, if you would look at average performance or median performance, almost no difference. However, if you look at the tails of the subject where we do really bad, we basically improve them on all the datasets. Those are kind of PSG datasets. Those are two of our in-ear and around-ear datasets. So again, sometimes we completely fail because of we do rather poorly because of the bad or the challenging signal quality. By exploiting more information, you can reduce the errors and improve your performance. So again, advantage of deep learning. Would I say? Sometimes people then say, and this is a recent paper here from Ghent, one of the colleagues here, who said, like, actually, the old good machine learning can achieve the same performance as deep learning. And I don't disagree with this. Look, if we put a new baseline and you train and you try many new features, ultimately you will find the same features and the models that give the same performance. But what is the point? The point is not to find the best model. The point is to find a model that generalizes across multiple datasets and use all those tricks. So all the robustness and so on, and the ease of use of deploying this on different datasets, they haven't demonstrated. And also, for example, another advantage of deep learning is, okay, we always train, as I mentioned, on a PSG dataset. There are many wearable sleep devices coming now. And every time you have to retrain, and I hinted already, if you have 10 subjects, retraining a deep learning model might not be the most convenient one, but you can also exploit information extracted from PSG in order to learn results on different datasets. In this study, we used kind of 2 electrodes behind the ear, one on each side of the ears, and a reference electrode, you see, so it's almost invisible on the recording, which might enable long-term recordings and long-term sleep staging across multiple days. Again, you can apply your model directly from PSG to kind of your new wearable data. Doesn't really perform very well, but if you add a few retraining steps, you quickly get to kind of new models that kind of perform relatively well and almost as well as you just train on all the recordings if you had them available. So again, all those tricks, they're now standard available in deep learning, and basically you can quickly get good results on new datasets. What I also think is important in deep learning, and again, there's a lot of literature there, is uncertainty. If you make a decision, it doesn't matter if it's right or wrong. It is actually a probability, a confidence. I make this decision and I'm certain I'm making this decision, or maybe I'm not so sure and the human can check it. And so this is actually another way, as explained, a different way from explainability to gain trust in your model. Give the confidence, give trust to the model, and maybe if you're not confident, just say like, look, I screen 90% of your data and the human does the final 10%. And actually, there is also a lot of uncertainty theory coming out of all the deep learning work. And actually, we differentiate between what we call aleatoric uncertainty and epistemic uncertainty. An intuitive way of seeing this, if you try to fit a curve through your data, this data is generated from a sinusoidal signal. And you see that there is some noise, some data noise on your signal. Obviously, you cannot reduce this because you see there is some uncertainty. However, sometimes a different way of generating uncertainty, of having uncertainty, is if I suddenly would look what's happening at this x value of 12. I don't have data to train here. So basically my uncertainty here is much larger and I cannot make any reliable prediction. I'm just lucky that I'm still fitting such a line, but my function could also go down and I could generate a large error. So understanding the difference between data errors and model errors is quite fundamental into the search of, into the understanding of uncertainty. And so what we can do, just to give you a hint, is we can look at the confidence in our model during training. And so what you would like to have is that your confidence improves. You learn from the data. But if you look at all your data samples, some will look like this. In the beginning, you have a certain confidence, but over time, you don't get more confidence, and the overall confidence is not good enough. So those are the examples that a bit annoy you during training because you can never get them right. So what you can do is leave those out, and what you can see then is basically also, is that if you remove some of those samples, your overall accuracy will improve. And that makes sense because those data, you don't learn from them. Maybe they're mislabeled, maybe they're very noisy, whatever. So you can use uncertainty on the one hand for during training, and on the other hand, you can also use them in what we call active learning. We find the most unreliable labels, we give the labels to the human, and the human can give some annotations for those segments and further improve model performance. I still have a few minutes for the other example, and I think epilepsy, the challenge is a bit the same. I think everyone knows what is epilepsy. Some people with epilepsy have to fill out an epilepsy diary. So when did you have a seizure? It's rather unreliable if you've impaired awareness seizures, which happen quite a bit. So again, can we think about a device that monitors brain activity during the day in order to automatically say how many epileptic seizures do you have during the day? Does your medication work? Does your medication not work at all? And so can we differentiate between epileptic seizures and no epileptic seizures? In the case of tonic-clonic seizures, we can do this. We can look at the EEG, we can look at other modalities, ECG, EMG, and we can look at accelerometry. We get a lot of physiological information, and you see that during the seizure, it evolves, and we can use all this information to extract features to build a simple classifier. We do this, we can fuse this information, and again, we have a reliable system. You see, I'm relying on multiple modalities. So I'm relying on a sensor behind the ear, maybe a sensor on the heart, maybe a sensor on the muscle. And what happens if some of the modalities are missing? Your system doesn't work anymore. So here we can use, again, deep learning, and in this case, we use cyclic transformers, where we learn actually the relation between, in this case, EEG and EMG. So how does brain activity relate to muscle representations in a way that we translate EEG to EMG and, EEG to EMG and back to EEG. And you would say like there is no one-to-one relationship, but there is still commonality because the EEG drives our physiology. And so we look at the mismatch between our real EEG and the reconstructed EEG, and we can additionally also train a classifier on the representation of the EEG in order to detect the seizures. And what you see then is that this is what we call the cyclic transformer or a multimodal cyclic transformer, that we get very good accuracy with low false alarms. And that also for a data set where we have only one of the two modalities available, we still have good performance, while in the other case, if you rely on feature fusion, like in a classical way, you don't have it. So again, an advantage of deep learning. But there the good news is ending. I really want to show you another case where we look at focal epilepsy, a different type of epilepsy. You see it happens with some high frequency activity, sometimes muscle artifact on the channels, and you see the signature of a focal epileptic seizure is very different, very difficult, very different between patients, and still we want to make a patient-independent classifier. We can do the same. We can look at features. We can even reduce the intelligence and use automatic feature generations in order to make a classifier. And then we can also use, again, multimodality, integrate information across different modalities for having better sensitivity, detecting all the seizures. All feature-based, always our baseline. And then we can say, okay, why don't we build a deep learning model? So obviously we did this. We tried this. We tried all the models we have, all the models that are published in literature. We couldn't beat this. If we can do it, we thought like, okay, why don't we do a seizure detection challenge, which we released for an ICAST conference. And we said to everyone in the world, here's our data. Why don't you build a model? And everyone could choose. And so our benchmark was 45. And there's one model that had a score. This is a score, non-interpretable. This was basically our model, the benchmark we set for detecting seizures. It was one contribution that slightly beat our contribution, still not using deep learning. And there were a zillion of other participants who tried their models, lots of deep learning, and we didn't beat them. So the conclusion of this is, it's about the data and the labels. It's not always that you have better performance. And I always advise people, start with the baseline. Don't start with deep learning as the first go because you don't know where you should end. But I think also the question is not do deep learning or not. question is more like use real intelligence to understand your problem and think about all the aspects like uncertainty, robustness, and so on in order to find the best solution for your problem. And as you see in the sleep case, deep learning has definitely some strong points that you can harvest, and the point is not to regenerate other feature-based models in order to beat this. Thank you very much.
Thank you, Maarten. Fantastic talk. Now we have our usual 7 minutes break, and we'll talk more in a few minutes. Okay, so we have a few questions for you, and let me get them here. Okay. Inter-rater agreement on sleep stage scoring can be poor, especially at the transitions. How do you deal with this?
The sleep stage accuracy on transitions is less relevant because, again, like in your overall performance, there are only a few transitions, so your overall metric will be still good. The model will always learn from kind of overall annotation. So once in a while, having a wrong annotation won't harm the method. In another project, we also worked on like correcting wrong labels, and then I think in sleep staging it's even a debate if it's wrong or it's just due to inter-rater subjectivity. But so overall, it's really not destroying the performance. Also because we have so much data to learn from, so many good labels that it won't harm the performance.
Mm-hmm. Okay, thank you. Uncertainty methods can be crucial in medical EEG classification. Why are they not being used yet? Or are they?
But the question is deep learning all being used and AI being used before we go to uncertainty in medical data, right? The reason is people want to be sure that it works. And then again, like what we typically have is one data set from a local hospital, and we can train and show kind of what we can do. In order to show that it really generalizes across hospitals or across settings, it becomes more tricky. And then what you see definitely from imaging literature, that even the smallest scanner settings can have a huge influence on the performance of your model. And because we don't all record, like even in the EEG case where everything is standardized, there are different amplifiers, different settings, that we have to go through all those regulatory and hurdles and definitely show that it works in all settings that we imagine, which is again like beyond a bit the research proof of concept we do. So I think definitely there we have some challenge. Also, there is an open challenge also being taken at the European Union, and like, okay, who's responsible for performance of AI? Because we never have independent AI, but still, if the AI gives makes a decision, a doctor approves a decision, is the doctor then responsible or the AI? So that's definitely two things on the AI. And I think there the uncertainty will help to navigate a bit the space, but we still have to take some hurdles to make it generally acceptable and relevant.
Okay, thank you. Very interesting. Can we know if different devices, scalp and around ear devices, use the same different features, or the same or different features?
I would say if you think about deep learning learns the features based on the structure in your deep learning model. So we apply exactly the same model on scalp EEG and EEG and ear EEG or in ear EEG, around ear EEG. So the way we generate the features is definitely the same. Obviously, they are going to be adapted to the signal morphology. So if the ear EEG signals are smaller, then probably the feature representations are going to be smaller, but they're still going to be related. We can also, what we did in one of our papers is also trying to learn simultaneously from the scalp EEG and the ear EEG. If you then look into the feature space, you see like the optimal ones are different. However, if you learn them all together, then basically you can also align the feature spaces and then they become super similar. So you can constrain even more that they are the same and performance is the same. So I think like the small variations we see are due to optimization and not really because somehow we're tracking something completely different.
Thank you. It seems surprising that the electrodes around the ear are so close together. Can you comment on that? How much do you get from electrodes that are so close nearby, right?
Yeah, it's a good question. So the history of it is that the first in or around the ear devices were in-ear devices, and they tried to place all the electrodes inside the ear canal, which means they're super close to each other. When we started experimenting with this, it didn't give us good signal results exactly for this reason that they're too close to each other. They're close to the brain, so that's good, but actually the reference electrode is so close to the signal electrode that there is no different signal anymore. And then we started placing electrodes above the ear, and we were measuring still in the ear canal. And like the best signal you had if you place the reference on top of your head, because then you had like a huge interelectrode difference, which gave you a huge amplitude. Obviously, it is not really ear EEG anymore, although you're measuring within the ear, it's still like the difference between the two electrodes. So that's where we started thinking, like, can we place electrodes around the ear? And definitely because the sleep waves are large. So basically in deep sleep, the amplitude of the waves become larger. The interelectrode difference is really not a problem. And that's what you also see now with the work in auras, that they can really get good in-ear EEG, even where they sometimes look at difference between left and right ear, which is again like a reasonable distance in order to get your signal quality up.
Okay, thanks. Talking about sleep, can we use deep learning not to categorize sleep stages, but instead to generate a more continuous signal related to sleep?
I'm not sure what's meant by continuous sleep, because I think the way sleep stages are defined is by human knowledge and the experience over time, and there is an Academy of Sleep Science that really defines the standards. I'm not entirely fan of it. I think we should rather do something as sleep quality, but it's not continuous. It's not a continuous thing across the night, but more like, okay, one or a few measures across the night, which are not uniquely related to the sleep stages. So yes, we can. The holy grail is that we find new features, new biomarkers for disease, maybe new biomarkers for sleep. But if you go back to the early slides, the best deep learning and the best machine learning models in general, they learn from labeled data. So everyone wants AI to be smarter than the human. I think we're very good at automating the intelligence we have the human. And so it's the dream there, but we're not there yet to just say, oh, here is data, give me now the new biomarker, because we're not there, but it's an open challenge for everyone attending.
Okay, work in progress. Is it still possible to understand how the deep learning network performs the task to compare it to how a human rater scores the stages?
Understand the task. So maybe the question goes again into interpretability, which is a question that Hubert also addressed. Yes, there are ways to look at what the network learns. Overall, it confirms like what the human is looking at, like definitely like slow sleep, deep sleep is slower waves, higher amplitude. So we can relate this, we can confirm this is being done. However, also in deep learning and machine learning, there is in general a trade-off between interpretability and performance. And so the best models, they're super complex, so they're non-interpretable anymore. And then there's always the question, like, yeah, do you want to have something that's completely interpretable or something that really does a great job? And so again, as long as the human is the standard, we cannot beat the human. And also interpretability will be something that we ad hoc can add, and sometimes interpretability is used for the developer who wants to confirm that the model is doing what it's supposed to do, and I think there we can confirm that overall it matches. to give like on an individual epoch, like this is the reason why I classify it, that's very hard. And they're like I always think about the whole night. There's so many epochs in the night. I can always generate 100 epochs where you have a perfect explanation, but also 100 where the explanation is a bit more difficult. And those are typically not shown in papers, but they exist.
Okay, thank you. What applications would there be for deep learning to generate patient data? And related to this, how would machine learning or deep learning based methods receive medical certification, also considering potential relearning?
Considering, what is the end of the question? Also considering possible?
Considering potential relearning. I'm not sure exactly what that means.
Yeah, I think for synthetic data generation, also for synthetic EEG generation, there is quite some interest nowadays in generating synthetic data for data sharing purposes. So if you have a clinical data set, can you share it with a larger community without revealing the identity of the patients and protecting even better privacy than with just anonymization techniques? There's definitely one ongoing research direction. There's still challenges. I think there are proof of concepts both for tabular data and for imaging data, probably less for time series data like EEG, also because the continuous time dependency, how it's realistically imitated is more challenging. On the other hand, you can think about rare diseases and augmenting your training set. But there, the challenge is you always have a limited training set that you want to augment, but you're still learning from your data. So it's not that you can really extrapolate and generate unknown EEG data sets that are realistically just from data that you haven't seen. So I think it's definitely a good use case, but I'm not aware that they're like groundbreaking work that really generates lots of data and boost performance in that way, because you can either put your intelligence in how you generate the data, or you can put it in the network to analyze your data. So it's not a free lunch.
Okay, still in the clinical context, beyond epilepsy and sleep, are you planning other clinical applications? What about neurodegenerative disorders from superficial EEG data, for example?
We are working on various applications. I would say from neonatal brain data to elderly, and also, for example, sleep in the context of neurodegenerative disorders is a very important one. However, it always depends on the data. So definitely neurodegenerative data, in order to really diagnose them early, predict them early, you need good data sets, and they're not there. And so in order to really collect data sets from conversion of still a healthy state to kind of an early disease state, it's hard to do this without screening whole populations. And you always have to think, okay, where do I find my data and the data in the ground truth labels, and then all the confounding factors. So yes, we're interested in it, but keep aware we can only learn from data and not invent new things without the data. Of
course. Okay, thank you so much. I think we're good, and we can close this session, this talk right now. Okay, we're gonna have a 15 minutes break for everybody, and we'll be back on stage here then. See you then. Thanks, everybody. We are headed for our final global session with Radoslaw Cichy. Thank you for being with us. And Radoslaw is based in Berlin, in Freie Universität, professor head of the Neural Dynamics Visual Cognition Group. Well, Radoslaw, the floor is yours. We are headed for the final session. Thank you.
Yeah, thank you very much for inviting me. I think you have created a quite innovative format for scientific interaction, and I'm happy to be part of this. I'm the last talk in this session and the very last talk. So I will stick to 20 minutes. I will try to complement the previous 2 talks. Some of it will be repetition, some of it will be different perspectives on it, on how to use deep neural networks and MEEG. The lab that I'm part of focuses on a particular theme, and that is object recognition, and shortly defined as how does the brain translate the constant flow of photons hitting your retina into a meaningful percept of the world consisting of objects. And we want to know how the brain does that. So with this focus, I would like to bring you up to speed on what the field is up to now in 2 slides. One is on connectionist modeling, and one is on why neuroscience might care about this. So, my slides work. Connectionist modeling has lived many lives and died many deaths, but it's its newest instantiation. I think it's here to stay. So deep neural networks, as you I think by now all know, are engineering models which are inspired by the brain. They have units that of neurons, they have connections, they do parallelistic computations. But they were built for engineering purposes. So they are supposed to solve some problem that a machine is supposed to solve, and they were not made to solve neuroscience questions or to be used on EEG. And since they've been introduced, they have outperformed any other existing model on particular tasks. So they actually came back to life in computer vision, where, for example, one very famous task was to predict what category of image you're seeing. So what you would do, you would put in a stimulus, for example, here of an orange, you would fit it through such a deep neural network, which is divided up into layers, which are supposed to mimic human visual areas, which implement, let's say, biologically inspired mechanisms like convolution, max pooling, normalization, and they would then spit out something like a category label orange here. And as you can see on the right side here, they outperformed any other existing model that was there. And actually by now they've improved even much more, and they are at human level for this very particular problem. Okay, I mean, that's great for computer vision, but why do we care, right? We're not computer scientists. But the idea was, we started wondering, well, these things do a task incredibly well that we want to understand how the brain does that. Before that, we didn't have such an artifact. We only had brains, and now we have something else created in the computer. So can we learn something from these artifacts and transfer it back to the brain? And that then became the first motivation to start comparing these things. So what people started doing is, for example, you took a stimulus set. This is some work we've done, 118 images, natural images cropped. You would show this to a trained deep neural network, trained on classification, and you would show it to human brains and measure them with MEEG or fMRI, with eyes and humans around them, and then try to see, okay, do these things have similarities between them? Can you predict one from the other? And because we're here in EEG, let's focus on the temporal dynamics. So let's say you show an image at 0 milliseconds, on the x-axis time, on the y-axis, how much artificial representations in those neural networks and your brain correlate, and you find first that all layers predict brain activity in EEG. So that was quite surprising. And also, if you just match the hierarchy of the processing, layer 1 is closest to the image, layer 8 is more complex processing, closer to the outcome, they actually also have a relationship to the peak latency, the fMRI. So also the order of the emerging representations for DNNs and cortex correlate. Now this works well for time, so it should also work for the spatial domain, and this is also what people found. So here you see, for example, an 8-layer network, and where it predicts brain activity best. And as you see, the early layers, layer 1, 2, 3, explain activity in the back of the brain, early visual areas, and the higher the layer, the more you move up forward in the hierarchy towards the dorsal and ventral stream. And this has been reproduced endlessly. So we know that deep neural networks predict brain activity in both space and in time. They also reproduce the processing hierarchy in the steps, roughly. And they do also, importantly, better than any other model class that is there on Earth. And that was also one thing. It's not just some other model. It's actually much better than anything else. But that has created this excitement. So now I would like to show you what else we can maybe do with it. And I would like to highlight a couple of projects from the lab. So the first one is going to be mirroring a bit of what Hubert was talking about predicting visual EEG responses to images. The second one will be how we can use this maybe to explain brain representations a bit by revealing their format, and we will focus on 2 applications. One is what is happening in imagery and perception, and what is happening during development. And then I will show you some ongoing work where we're trying to model EEG responses, not to images, but to become a bit more complex and go towards visual events. Okay, let's start with the first one. This is work by Alessandro Gifford, a PhD in the lab. So in the previous case where I showed you where we compared brains and artificial networks, we had 118 images, and that's not very much. And we had a discussion here locally saying, okay, how many parameters and how many data points do you need to meaningfully look at deep networks and brains? And we thought we actually don't have enough. We need much more. So let's get much more. So we took the same image set that we used, the things data set, but we recorded our own data in a different way. So we have 1,654 different object categories, and we take 10 exemplars of this, and we use this for a so-called training set. And we have a separate test set, because as you learn in machine learning deep nets, you always have something for training and for testing, and they need to be separate. And we have a test set of 200 separate images. Now we want to get lots of data for this, so we use them, or we show those images in a rapid serial visual presentation stream. So an image is on for 100 milliseconds, 100 milliseconds off, 100 milliseconds on, 100 milliseconds off, for 7 seconds. From time to time, you see an image of Buzz Lightyear. This is, Alessandro's signature object. And if you see that, you need to blink and respond whether you saw it or not. And we do this for quite a long time. So then we record actually EEG data for about 16,000 image conditions, which is about 80,000 trials per person. We have 10 persons, so that's about 800,000 trials. So yeah, we are actually, if you think about in terms of instances, we are kind of getting to where ImageNet is. Okay, so what do we do with this data? We use a so-called encoding approach to predict brain activity. And it's actually very, very simple. So you take those images and you show them to human beings and you get your biological data, EEG, for example. Then you take those same images and feed it to your deep neural network activations, and they're just going to, calculate them, and you're going to get those activations. Then what you do is a simple linear regression. You predict one from the other just by fitting a line. That's so simple. And once you've done this, actually, you can use this regression to show other images, and based on the mapping you learn, predict brain data. And by then comparing the real data with the predicted data, you can see whether you actually predict correctly, and you've learned something, or whether you just learned noise. So let's see what happened. It actually worked quite well. So on the x-axis, you see time in seconds. On the y-axis, the correlation between the biological data and the predicted data by the neural networks for 4 different networks. Doesn't matter, they all do the same, no differences. The gray line is an estimate of the noise ceiling, basically how much signal there is at all to be explained in the EEG data. And you can't do better than this. And actually, in the early stages, until about 200 milliseconds, we're explaining all there is to explain. And later on, we don't do that well, but we still do pretty well. So yes, using this approach, you can predict EEG data pretty well. This is an average across 10 subjects. And you can do this for every single of the 10 subjects reliably. So actually, we could also have written the exact same paper on one subject, but we didn't know then. And we're actually happy to have this data because now we can do other things with that. Okay, to maybe convince you that this is actually a useful thing to do, you can ask the question, okay, you can distinguish your 200 test images, but that's not that cool. So how many images could you actually predict in principle? So we use something called zero-shot identification. We take lots of additional images for which we don't have the brain data. We feed them into our prediction mechanism, and it's going to predict us biological data. And now we're just asking, can you still pick out the true image from the brain data? So if you feed in lots of images and your prediction is bad, at some point, some random image should become better than the real one. So how many can you feed in? On the x-axis, you see how many images we started to feed in. On the y-axis, how good we're doing. So if we only look at our 200 images, we are at about 80%. And if we start adding more and more and more, let's say 150,000 images, we end up with about still 20% decoding accuracy, where the chance level is 0.05. So if you start fitting a curve to this, we couldn't just keep on adding millions of images because this takes a lot of time. If you extrapolate this, this would mean that you reach the 10% curve at about 3.615 million images, and you reach the chance level for your 200 images at 16.2 trillion images. This is just to say it really works if you really want to predict brain data in whatever context you want. It doesn't have to be images, it could be something else. This is a valuable approach. It's going to give you strong data. The last step we did with this, again, mirroring Hubert, then asking, okay, this all relied on a deep neural network that computer vision scientists created for different purposes and we reappropriated that. Can we get rid of this? And the answer is yes. So if you have enough data, you can just train a network where you feed in an image and you train it to output EEG data. And this actually works. So on the x-axis is time, on the y-axis is how well you're predicting the data. And with sufficient data, it's absolutely possible to train deep nets from scratch with no pre-training whatsoever to predict brain data, which gives you a lot of power, for example, I don't know, even envisioning something like prosthetic devices or maybe experimental control. Okay, but this was all about prediction, nothing about explanation, understanding the brain per se. You can use this for understanding, but by itself, it doesn't do it. So I would like to highlight work by seeing here, who has tried to do this to reveal the format of visual representation. I will give you 2 examples of how this may be done. So Seeing did an experiment, and there was some question about visual imagery previously, and then she did something on visual imagery. She was showing these 12 objects to human beings, and they either saw them in vertical perception or they were auditorily cued to imagine things like that. Okay, and then we ask, can you decode using standard machine learning methods, which the last talk also discussed, what people are imagining from what they're seeing? So we do this for all time point combination. On the x-axis, you see the time of EEG and perception. On the y-axis, the time and imagery. And this is in one particular frequency band, the alpha band. And we say, yes, we see that we find shared representations between imagery and perception. It means you can predict what people are imagining from what they're seeing in this particular time frequency cluster. And this is actually limited to the posterior channels and not the frontal channels. But this is actually really a bit more likely a visual than a frontal thing happening. Now that you think, okay, we have those representations and they are shared between imagery and perception. So what are they? Can we say anything about that more? So your Seeing said, okay, let's do the following. We're going to take a deep neural network trained on visual object classification. If the representations are similar to this, then the representations are of visual features. Or we take a semantic model, which only cares about the category of the objects. Then it only cares about semantics. Or we take an audio model, which cares about speech and the auditory features in it. And then what we actually are having is something like they're saying the word in their head like apple, right? That should be the predicting thing. We use something called representational similarity analysis. If you attended Sari's and Gemma Rod's and Danik Burse's workshop yesterday, I think they used this as well with their toolbox. But this is just another tool to compare representations. What they find is that the representations shared between imagery and perception are not predicted by spectrotemporal auditory models, not by semantic models, and not by a deep neural network trained on audio categorization, but by the late layers of a deep neural network trained on object categorization. And we know that these last layers of those networks have complex visual features. Now we can say, yeah, what is shared between those two is actually complex visual features. This is the format of those representations. So we learn something about the brain. A second example here, also worked by Seeing, was trying to understand how visual representations come about in the brain. So usually we measure visual representations in adults, students that we can measure in forever and are well controlled. But we started caring about infants. So we started measuring 6 to 8 month old infants with EEG. And just doing, again, classical machine learning, we want to think, which of these 128 images or 4 categories are those adults or infants seeing at a particular time point. So on the x-axis is time, on the y-axis decoding accuracy, it's pairwise classification of 50% is chance, and you see that about 60 milliseconds, a very steep rise in the curve and a decline, as classically see in adults. This is how we process, that's the time course with which we process visual images. But you can also detect a significant curve in infants, and that's quite amazing given how crazily bad the data is, right? I mean, they don't follow orders, they don't understand your orders, they move around, they fall asleep, but it works. You can still get something done. And the topography of where this information comes from also makes sense. It doesn't come in the infants from eye movements only, it's actually coming from the back of the brain, so this might actually be real visual data. So again, we're asking, okay, cool, we can decode this stuff, but what is the underlying format of what we are decoding? Are infants and adults the same? So here, Seeing, same deal. She takes those images, and here just a very simple thing. She fits them into a deep neural network model, again, trained on visual object categorization. And then asks, okay, which of those layers predict the activity in infants and in adults? And as you can see, you see a very, very similar pattern across the layers. And the layers just stand in for something like processing complexity. The early layers, we know, have something like a Bohr filter, so that's low complexity. The late layers represent object parts, combinations, so higher complexity. And the two graphs are pretty much identical with the exception of layer 7, which are high-level features. So what seems to be the case is that infants and adults discriminate categories, but based on partly different features. Infants at 6 to 8 months don't have yet those high-level complex features, as you would expect maybe due to the myelination pattern of cortex, but this is something that you can now explicitly show. Okay, I would like to then focus on the last work, which is just ongoing work. It's just a little teaser. We have not done much on this, but this is something we started because we wanted to go beyond just showing single images. Your visual experience is not of unordered single images. You look around and there is more complex stuff happening in the world. Now you can go to full complexity to, I don't know, like long feature movies, but we didn't want to go there. So we went to something we called little events. So these are 3-second movies of stuff happening, like a baby laughing or soldiers marching or a panda eating or something else. And then we said, okay, we're going to take 1,000 of those videos as a training data. Again, we know training and testing. 102 of those other videos that show different events for testing. And we're going to get brain data for this. In the lab, we often work both in space and in time. So we get most things for fMRI and EEG. The fMRI data was this is out there already, published by Ben Lahner as a preprint, which is under review, and the EEG work is ongoing. So we actually record brain data for those videos. Now, videos is something you can't speed up with RSVP, so it actually takes some effort. So right now I have something like 8 sessions per subject. Every session is about 2.5 hours. We're ramping this up to 16 sessions per subject of about 2 hours. So as I said, you need a lot of data, and sometimes I think we shouldn't be so lazy getting it. Although it's not so pleasant to get it, but once you have it, it opens maybe a new world for you. Okay, to capture the content of these complex videos, we need something that is more than just a category or a simple description. So we actually asked, that's just one example, asked participants to describe what is happening with those videos. And here, for example, are 6 different captions, what people said about what's happening in this video. And then we want to map those linguistic captions on those images and predict ED data. So how do we do this? We take those video captions. We have 5 or 6 for every video. We put them into a deep neural network model based on a language model, basically what you know as a large language model. We could have taken GTP 3 or 4 if we had it and it wasn't too big. So we had to take something smaller like BERT, which also works, which gives us an embedding of the meaning of those sentences in those models. These are 768-dimensional semantic embeddings. Now they're a bit too big, so we use PCA, we make them smaller, we average them, and then we use this to just, again, make a simple linear prediction of the EEG response. Then we see whether we can predict the EEG data from what people said is happening in those videos, not the pixels, just the words. And that actually seems to work quite well. On the x-axis, you have time. On the y-axis, the Pearson correlation between the predicted and the real data. And you see, around baseline, before things are shown, there's nothing happening. At 100 milliseconds, the curve goes up, then it declines, but it stays pretty much significant until 3 seconds. And even this, for us, was exciting to see because we know what's going to happen if I show you an image. But I have not the slightest idea what the EEG signals will actually look like for longer videos. Of course, there's going to be adaptation on the one hand, but on the other hand, there's lots of complexity and things are changing. So how is that signal going to look like? How are we going to analyze this? I don't know. So that's, that's a nice new frontier to go towards. You can use deep networks as exploratory tools to start looking at that. And because you have time and coupling things, you need to capture this complexity, and deep networks that work on language, which can describe complex relationships, can help you. Now, if you want to start this yourself, there's lots of stuff out there. We have conducted, for example, an online prediction challenge where we give you brain data and you can use whatever model you want to predict the brain data online. And there's a full development kit for doing this. So you can load and visualize the challenge data, that's fMRI, but you can very easily adapt this to EEG. You can train and test encoding models. You can prepare the challenge videos, and there's videos to guide you through all of these steps. So this is also great for learning purpose. Either you or your students can just go there and can learn that by themselves. And the second one is there was a workshop yesterday by co-workers of Gemma Roch, which showed you how you can use the Net2Brain toolbox, which has gives you the ability to test hundreds of models very fast against also EEG data. And there's tutorials there as well, so you can use that too. Okay, so to shortly summarize, I think I've argued that first, DNNs allow you unprecedented prediction of human brain activity from EEG, even end-to-end, mirroring Hubert's talk, merging also the last talk. I think we have really convergent evidence of the power of this. So there's very strong predictive potential for experimental control and maybe visual substitution. Second, I've shown you that DNNs can be used as tools to reveal the format of new representations. So there is some explanatory potential for understanding what is actually happening there in the brain. And third, I've shown that DNNs can support the analysis of EEG, capturing neurally and temporally complex stimuli like short events. So there is some exploratory potential to understand the new representations where we actually don't know what's happening and how to go about this with some increased ecological validity. I would like to highlight the three people that did that. These are three PhD students from the lab, Ale, Seying, and Pablo. And of course, ask the people who do the job in the lab, which is the lab and the funding body. And you. Thank you.
Thank you so much for this great talk. And now we're going to have a few minutes break, and we'll see you again in 7 minutes. Thank you again. I was told that my thanking you at the end of your talk seemed a bit like unenthusiastic. It was not meant so.
I felt highly appreciated. No, it's good. I felt highly appreciated. All good.
Okay, cool. All right. So we have a bunch of questions for you. Okay, we start here. Is there any way to reduce the amount of data needed to train models? This seems to be the main limitation to apply this method for BCI or any other application, actually.
Yes. So I mean, we're trying to push the field or ourselves to record as much data as possible, but then we can also subsample it and try to find out how much do we need, how far would we get with a lot less data? Should we have more trials with the same images or less trials and more images? All these questions. There are no numbers I can give you. So I think the first step is always record a lot of data, start subsampling and see how far you can get. Even for clinical applications, right? You would want to create a gold standard where you record your patients in a laboratory setting for 2 hours, and then you subsample the data and say, instead of 128 channels, I'm going to have 16, and instead of 2 hours, I'm going to have 30 minutes. How far do I get? So we make this, I have no answer, so we rather make this a research question.
Okay, and it's ongoing project.
It's also a question of the field and how much it buys you, right? If having a lot of data is still outperforming other approaches, you're good. If not,
yeah. Okay. Is it also possible to localize specific visual features in space with EEG, not only in time?
Yes, sure. So the way we typically do it is we just say, we don't care about space. We just do the predictions across a subset of electrodes. If we care about visual stimuli, we just take the electrodes overlying parietal occipital cortex, or sometimes just all electrodes. We just throw away all information in EEG that's there about space. Now, EEG isn't, you can still do source localization with EEG, but you could use MEEG, which arguably has better source localization, or both together. And there's nothing that stops you to project your features onto the cortical surface and then use all the things that you've seen here on the cortical surface. Then you would get a space and time resolved image. Of course, by doing this, you are strongly reducing the power of your approach, because you are only subparts of the data that you record are going to end up at any particular point. But by itself, if this is something you care about, yes, absolutely, you can do that.
Okay, thanks. What metrics did you use to compare the generated EEG with the real EEG data?
Correlation.
Thank you. How long does a typical experiment with EEG and images last? And related to that, what is the online feasibility for BCI applications? That kind of relates to the first question in a way, right?
Okay, how long does this take? As long as we can. So, no, it really depends on the application. I think you can get great results with 1 hour of EEG data. Now, if you're talking about BCI, what BCI application are you thinking about? Are we thinking about a locked-in patient that you want to try to make talk to you? Or are we talking to someone who just puts on some cap and wants to play a video game and you have 5 minutes? If you have those 5 minutes, no, I don't think it's going to work. If you actually have a hard case, it's, I think, worth investing the time. So if you invest 2 hours and then you can talk to that person well, that's worth investing the time. But it's I think a lot of the BCI field has tried to do something that works out of the box or with minimal intervention. Mm-hmm. I don't think that's going to work here that well. That might be wrong. Hubert in the second talk said, look, you can do across subject learning. You can maybe create those networks pre-trained very much, and you don't need 30 hours, maybe 2 hours on tops is just enough. This is not something we have tried.
Okay. Does the internal state of the subject influence the results?
Sorry, I don't see
guys, can I have the next question on screen? All right. Okay, so it's the same question, but number 2 here on screen. Whether the internal state of your subject influences the results.
Whether the internal state of the subject influences the results. I would expect
attention, emotion, I guess.
Yeah, I guess. I mean, once you're in there for long enough, you end up with a very particular set of emotions that's always the same for everyone. I presume. Now we have tried. Collaborators and others have tried looking at this and seeing how much doing a particular task influences your visual representations. So we showed the same images to human beings, and they had 2 different tasks, which we called, like very classical cognitive psychology, semantic tasks would tell us the size of this thing, or whether it's animate or inanimate, or physical characteristics like has it a blue outline or tilted left or right, for example. And we found a minimal influence on the early response and a really small influence on the later responses. So this to us tells us that we're really tapping here into very automatic processing that is not yet very cognitive. But once people fall asleep, that's going to stop.
So, but even at later stage, that's quite surprising, isn't it? Like that later time windows are even less predictable less mapping than the early ones. Right?
Yes. So we both find that we can predict the later stages less well than the early stages, so that might point towards a more cognitive involvement or more trial-by-trial variations which we don't take into consideration here. It might also be cognitive factors. So yes, the later in the time course, the stronger the cognitive factors. But again, compared to the grand average or the area under the curve that we're predicting, this is a pretty small part. So it's not that there is some reversal. At some point, it's all predicted by the mental state or the emotional state and not by the content.
Yeah, of course.
It would be a good experiment to do this in anesthesia, but it's hard to do. And I would predict the early response are going to be identical.
Yeah. Okay. You showed us that you can predict EEG from a picture. Is it possible to do it with a video directly? So
we have not
EEG from a video.
We have not tried, but I wouldn't see why it shouldn't be possible. It's a bit more of a complex problem because now you have time in 2 dimensions, in 2 aspects. One is in the video is changing and the EEG is changing. With the image, the image is not changing and just fitting it for every time point, and it's great. Now you have to map the time of the video to the time of the EEG. And it's not clear how to do this, and that's exciting actually, right? Because it's probably not a 1-to-1 mapping with a 60 millisecond delay. But some areas respond later, some respond earlier, some will have short integration times, So they just respond to changes at 10 to 100 milliseconds. Others will have longer integration times. They'll integrate information over 300 milliseconds. And how to map all this is an open question. So it's something we're asking, or hope to ask.
Thank you. Are there more potent features for decoding? So if there are multiple features such as color, luminance, semantics, etc., is it possible that some features could dominate and others would be missed by the network in some way?
I'm not sure I understand the question. I mean, yes, so these networks, even if trained on something that we believe is a definite task, are going to use whatever can be used to do that task. So if you, for example, would train this network to just do color classification and color correlate with anything else like orientation or whatever type of structure, it would find that structure in there, hopefully, and use that. So it's hard for me to see, and I think it's an open question whether in our brain neurons dissociate those factors or whether each neuron or the population code is mixed for all of those features. And I think that's a question both for deep nets and that's a question for visual brains, for which there are different positions. So again, a research question.
We were also wondering how we can reinforce the interpretability of the results when using deep learning methods with M or EEG. Do you have any recommendations or guidelines? This is our question.
Yes. So I think a good thing is before you start doing this, you ask yourself, why are you doing this and what is this going to tell you? Because you can use these deep nets in 100 different ways for 100 different goals. Some can be just predictions, some can be explanation, and some can be exploration, and you should just be clear about what you're doing. Once you start finding a particular, let's say, correlation or effect between those networks and your brain, you can then start asking questions, what about this network it is that is doing the job and the prediction, for example. And you can start, you can use any type of technique that is existing for understanding those networks. You can use, as people use electrophysiology in monkeys or in humans to understand your representation. You can also use exactly this thing in deep nets, and you can ask which neurons or units in there having a particular defined characteristic is actually underlying this prediction. You can use knockouts, knock out neurons or units in the network and ask how much is this impacting what I'm doing. You can ask about the crucial factors that influence what a network is doing, like the architecture, the training material, the training procedure, how much you've trained it, and start manipulating this. And this should then give you an informed picture about the factors that are determining the observations you're making. The answers might be very different from what you usually expect if you are on the single neuron level and you don't have a population, or when you come from a classical field where you have a priori predictions. But I think you can, by, for example, using these post hoc analyses, find out a lot about what it is about those networks that is doing the job. I hope that helps.
Okay, thank you. Can you show us an example of predicted EEG data?
No.
Okay.
I can't share my slides anymore, and I would have to look it up somewhere on the computer. But the funny thing is, it is going to be very hard for you to see any difference to the biological data, because actually, if you just want to predict the brain data without knowing which image it is, the correlation is going to be 0.999 because you're learning the ERP, and that's really nicely predictable. But then there's these tiny differences on top that are the differences due to the images, and you won't even see them, I think, with the naked eye. But this is where the job of the prediction is coming in.
Okay, a final question. Any potential applications of these advancements?
I think indeed, so we're not doing this, but I can only report on what maybe other people are using this for. I think there's a very clear idea using this for prosthetic devices. So let's say you lose a particular visual area, you need to plug in information into this visual area, and now you need a prediction of the input to this area, and now you can do this, hopefully, to some level, right? We're not talking about giving people back florid and rich sight, we're talking about maybe black and white perception. And then people are working on such implantation devices in non-human primates, and I think they started working in humans as well. We use this for experimental control. So for example, we want to then use these things and create stimuli that activate particular visual areas very much and others not. So let's say you want to know what V2 is doing or V3 is doing. So I want to have images that give me a particular pattern in V2 and a different activation pattern in V3, or that drive V1 very strongly, but don't drive IT very strongly, and vice versa. So I can start mapping and dissociating the effects of those two using particular stimulus material. This has been also done by several groups in monkey, and people start doing this, I think, in humans now as well. So that would be 2 applications, potential, one clinical and one in basic science.
Okay, thank you. I'm sure the military will think of an application.
Yes.
Okay, all right. Okay, well, thank you very much for this discussion. We will now have a quick break for you all to brainstorm your final questions for the whole session, and we'll see you in a few minutes. Thank you for sticking around for the last round of discussion. It promises to be quite interesting. Are there, do you think there are any limits to deep learning? They seem to be so powerful and capable of everything. What kinds of limits do you envision for the field at large now and in the future, I guess? And this first question is for, well, the first speaker, but you'll all speak together. Hubert, can you tell us what you think?
Well, I think it's a different question if we consider deep learning in general and deep learning for MEG, EEG, and neuroimaging data. If we consider deep learning in general, well, there's definitely, I think it's a very active question. People are wondering, can we reach, say, a human level intelligence just by ramping up the size of our networks, the size of our data sets? So yeah, definitely a very, very open question. For EEG and MEG, well, I think the limit is what information exists in the brain, what information we can access with the current neuroimaging modalities that exist. Especially when we think of surface EEG and MEG, we know that we don't access everything that's available in the brain. So yeah, I'd say yes, there are limits when applying these methods to neuroimaging data, potentially because of the brain itself or just the neuroimaging modalities we use.
Okay, thanks. Maarten, do you have something to say?
Yeah, I wanted to give exactly the same reasoning. It's not the limit of deep learning as such, but it's the limit of what information is intrinsically there. And we have signal and we have noise. And so what probably with a bit of improvement of deep learning, we can extract more signal, but what we don't record, we can never get back. So I think there is the limit, and only by improving the methods, we will learn what we can extract and what not. And we had here in Ghent also the discussion on what the inventor of the EEG, Hans Berger, that he wanted to use telepathy or something like this to decode brainwaves and things like this. We know now we're never going to get there, which is probably for the good. It's nothing with the analysis method. It's with, okay, how do we record EEG or MEG?
Thank you. Radek, any more, any other inputs?
I mean, on the one hand, these deep neural networks are universal function approximators. So if complex enough, they can solve any function in the universe. So they are unlimited. On the other hand, they are always highly limited. And there's a huge amount of things that many people point out, and we, of course, as well, that they can't do. And in a huge amount of ways, they are terrible predictors of the brain. Now, I think, of course, a good model of the brain in some way is going to be a neural network model, because that's what the brain is, but it's not going to look exactly the way we're thinking about now. What I, for example, talked about was so limited to mostly convolutional neural networks for the visual system. What about prefrontal cortex? What about hippocampus? How do these things fit together? So I think it takes a lot of ingenuity and creativity. But once we have this, we will have the solution. When this is going to happen, I don't know. Is it going to happen? I don't know either.
Okay, what can we learn about the brain from generative AI, like the work of Hubert presented? So in other words, where materials similar to the stimuli are generated rather than the input EEG. WTF.
Right, okay, so talking in terms of decoding rather than encoding. So I think, well, maybe one first answer to this is that by looking at generated images, we have a very visual representation of what happens during visual processing in the brain. So if you take a sliding window approach or a growing window approach, you get just another view into what can be shown otherwise with maybe decoding curves across time. So yeah, if you're trying to understand how the brain works, how visual processing works in the brain, that can give you just another window into exploring that. Yeah, maybe that would be the first, my first answer to this.
Any other comment from the two other speakers? Otherwise, I can, yeah, go ahead, Radek.
No, I was saying I'm not using generative AI yet.
Yeah, you're not using generative AI, so okay. What do you think is the next big model architecture in machine learning? Why do we keep using convolutional networks instead of exploring other possibilities like sequence-to-sequence model in the case of time series MEEG data in particular? Boom. Tough one or?
No, well,
go ahead, Martin. Yeah.
I think I only presented sequence-to-sequence models in all our sleep work, and I think definitely in neuroscience we are always 2 or 3 years behind the models used for speech and image. So we basically don't invent new models. We basically use, for example, transformers and things like this, which come out of different fields and are state of the art there. So that's definitely one comment. Yeah, we are using them. Obviously, the more complex your models, the more data you need. So that's also probably a reason why we're always a bit behind, because we need time to collect so much data. And I want to add, there was something I wanted to add here. It's also like, I also think definitely in the sleep, and I don't know what's the experience of the two other presenters, but I showed that even using a more complex model marginally increases the performance. So again, like, you don't need to invent another model for no benefit. I mean, if a simple model is giving you good performance, you should stick to the model and use it to the benefit of your example rather than doing this. And that's where I think, like, all the other things, there is more data-centric AI now being used rather than model-centric. So, like, how can we pre-process or handle the data in a smart way rather than just applying a different model for the same problem?
Comment. So, I'm not a machine learner, so I don't know what's the next big model architecture there. I couldn't develop it myself at all. But let's say, why are we using convolutional neural networks? Well, because they are easy to train, because you just need to train the same feature for every location in the visual field of the network. But there is people that say, no, we should stop doing this. This is not how the brain works. So there's, for example, great work by the group of Tim Kietzman, who said, let's get rid of this convolutional architecture. We want a network that learns different features at every location. And that actually works quite well. So I think research in, for example, this direction, getting rid of convolutions, which is difficult because you have so many more parameters, is underway and is working. And then you can, of course, also think about all these language models, which are transformer models, which are not convolutional in the classical sense anymore, and are a completely different architectural class. So I think we are right now in the transformer age. The CNN age is a bit over. Who knows what the next one is going to be?
If I can comment on that, add my comment on that too. Yeah, I think the reason why we keep using CNNs is what was said by the other presenters is it works well. It's not very heavy, and what we've seen over and over again in many different application areas of deep learning to EEG is that actually quite shallow, small neural networks will work pretty well and will get you most of the way to probably the best performance you can reach. And also specifically CNNs, we were having a little discussion about this in Bournemouth. CNNs encode great architectural priors for the kind of time series, multivariate time series that are EEG and MEG. And about what is the next big model architecture for ML, for MEG and EEG, I'd say there's definitely a lot of promise in scaling up transformers. So I know that Maarten's work on transformers for sleep staging showed a slight improvement. My current interest is how far can we push this if we actually pool all of the data we can find, right? And build multimodal transformers that not only rely on EEG, but maybe on MEG as well, maybe other related techniques. So we'll see as we scale up the data.
Yeah, and then you can also go to foundational models for EEG if you pull lots of data.
Okay, now I'd like to step out a little bit of all the technicalities that we've been talking about so far, and try to reflect a little bit on the ethical issues that issue with deep learning. And yes, I'm thinking in particular, and that's a little bit of self-promotion that I do of the talk that I gave at the beginning of the meeting here in Lyon about the ecological impact of those big infrastructures that are required to process, to train networks in particular. Also of the societal impact that us relying on more and more evolved machines to do our daily life has. So yeah, so the implication that it has. Yes, so I don't know what's your opinion on this, if you're reflecting on that. Ethical, ecological, perhaps both to go together. Yeah, who wants to start talking? Okay, Hubert, vas-y, start, please.
Yeah. Well, I can start. I mean, you raise a good point in terms of infrastructure that is needed for training these big models, especially in other fields like computer vision. We know that the models that are trained require a lot of hardware and are powered for maybe weeks to be trained. So this is definitely something that has to be taken into account. Luckily, in a sense, with EEG and MEG, we are a few orders of magnitude smaller in terms of data size and also parameter size. So these questions might not be as pressing for now. But definitely on that point. One thing I wanted to highlight here, maybe that was not the intention behind the question, but as we deal with this kind of personal data, because EEG and MEG at the end are personal data, we have to keep working with the safeguards that are in place, kind of ethics board, sorry. This kind of approval, this kind of process is still very much important, and even more important as we scale up these kinds of data sets. And so working in an open framework where research is reviewed and shared with peers, I think is very important.
Mm-hmm. Yeah. Next in line.
Yeah. Well, can also say the ecological thing is definitely something we have to worry about, and then I definitely think that we have to think about the Googles, the Metas, and OpenAI, because they have the power. Like, I think in an academic context, we're going to be relatively limited by the models we can train. So some major companies have almost unlimited power to train, so there they have an enormous ecological footprint, and I think that's definitely something. Also, there's research being done on how to train more efficiently all those deep neural networks exactly for this, which is definitely going to be critical in order to bring AI in general. We actually had exactly the same discussion here in Ghent on the ethical things. And my answer there would be, like, we don't have an ethical problem of deep learning or AI as such, but there are huge ethical consequences in a particular application. And so that's why you cannot stop AI research just because there might be a wrong application. I think we or regulators, policymakers, and so on have to think about specific applications and then regulate and think about ethical consequences per application or per application field or something like this, which is really hard because everyone thinks AI is the beast, but it's always how you use AI. AI as such, it only does how we humans implement it and use it.
Thank you. Yeah, I'm also deeply concerned about these types of like the applications that we don't fathom at the moment, and how those data appropriated by the big corps can be used in a deleterious way. I don't know, Radek, did you want to say something?
I'm hardly qualified. I can basically only repeat what the other two speakers said. I think concerning EEG and MEG data, we are still far away from a real misuse case. I might be wrong, but I don't see it. So sure, you can read out what people are seeing or maybe dreaming or maybe imagining or thinking from EEG data, but before that you must put them endless hours into a chair and make them fixate on images. So, if you're a really nasty guy, I think there are much faster ways to getting that information. What the future might bring, and that mind reading is a societal problem or a danger, is of course true, but I don't think anything has changed over the last 20 years in that. Also, many problems are just reappearing, right? So, of course, deep neural network training is an exclusivist club. Only big companies can do this. Universities can't do this anymore, and it's up to society to decide whether they want this to happen or not to happen. It's a question of regulation, and if you have this democratic power, we can regulate this. But even here, usually, experience shows until now that first huge models are developed that no one else can use, but it takes a bit of time, and then much, much, much smaller models that are similarly performing come out. So there is the hope that for the time being, this is limited to a few, but even those huge companies will need to scale down at some point and compress those models, and then they will become more accessible to others as well.
Yeah, actually, if I think about if you think about the concrete example in reproducible science, which is probably very closely related to what we do, like having those very complex models being trained and so on and so forth. So even with sharing, like, do we share all the code? Do we share all the details? Do we share all the data? I mean, it might definitely take a bit of time while a lot of engineers definitely share code nowadays. I think like the more complex we go and the more the optimization even depends on the seed, which again, like might happen, can cause some concrete impact. Just close to what we're doing now, but
and
how to regulate it. But even sharing data or sharing some code is not going to be enough.
Publishing such data in a fair way with following those fair principles is going to be a real challenge, right? Because making this data accessible in the sense of like anybody being able to use it in a transparent way is probably very difficult, right? Okay. Right. A question that seems to fascinate a little bit the crowds is about mind reading. How far are we from understanding the mind? So not so much about reading it, but perhaps understanding. That's a big question, and perhaps like you can freely fly from here if you want.
I think very far.
Yeah.
No, but I think when I think about it, it's also in a traditional EEG fMRI context, you had always very controlled paradigma. So you really had one test which you would record a lot of data. I mean, those more adventurous types of analyzing data allow to push a bit the limit of what we're doing, but okay, we're still having what is there in the data, what are the limits, and how do we analyze, and there's always going to be interpretability and so on and so forth. So yes, we're very far from understanding how the brain works, and definitely not reading minds, but it's definitely also enabling a few more steps, and I think that's what is the power of it. It helps us think out of the box, explore a bit more. Does exploratory data analysis, as nicely illustrated, and that's the good thing. And where we will end, I mean, depends on how many people explore those new tools.
Okay, thank you so much. I have a last question. It's a personal question, actually, because that's something we've been talking about at CuttingEG in the last months or so, preparing for, and I'm kind of announcing something here, preparing for the 10th anniversary of CuttingEG next year. We are wondering what is the role of the MEEG scientists in society. We are pursuing some knowledge, or like trying to gain more knowledge, but we're also trying to build devices with BCI, for example, that will entertain people, help them with their problems in life. What do I know? We have also clinical applications, all of this. What do you see? And you will be the three first ones to answer this question, which we may ask again in the coming year. So yeah, what do you see as our role as MEEG scientists for society? What's your favorite one, perhaps amongst those that I cited? I don't know. Allez, same order. Let's go.
Well, for me, everything that you said is actually, I think, part of the role that I think MEEG scientists should play or could play. Of course, there's the scientific endeavor part of it, trying to understand the human brain, understand the mind, which is very interesting. For me, what brought me to the field of brain-computer interfacing and neurotechnology in general was really the idea that could eventually help people live better and healthier lives through neurotechnology. And as such, I see all of the work that we're doing in machine learning and deep learning as a way to advance toward that goal. In a few words.
Maarten, do you have something to say?
No, but I think you did already a great role indeed in promoting and facilitating and sharing knowledge. I think that's the mind, and the applications are unlimited, right? And that's I think the nice thing. I even think about when we started with mobile EEG, we had like 1 or 2 applications in mind, and you see like other people take it in different directions, and that's the good thing, and that's also what I see in the deep learning now field and in every technology. I mean, someone comes up with an idea, and others take it forward in unexpected directions, and the more this can be facilitated and supported, the better.
Thank you. Radek, your turn.
I cannot speak for the community of scientists at all. I can tell you how I felt about it, not even about MEG or any research, but I actually chose neuroscience, maybe a bit of a sarcastic or cynical position of a young person when I was young, because at least it's useless. You can't, destroy things with it. It's not a weapon. You can't immediately misuse it for something else. I'm going to do it. It's really interesting, but it's at least it's not immediately used for something bad. That's a stupid infantile position, I guess. I think it has grown now to me that using especially those deep nets and this EEG, I have the hope, and we're trying this now, to actually use this for something good. So when we think there are diseases of the brain that also afflict the visual brain, and we can maybe build now devices that we have all this machinery and all this fancy stuff around that actually would allow us to diagnose people as to whether they have a condition or not, independent of language, independent of education. And if you can use EEG, which is way more cheap than, let's say, MRI or PET, also for a much broader range of people in the world. Most people in the world, the billions out there, don't have fMRI or PET to diagnose diseases. So I'm hoping, and this is something I really believe, and I'm trying to push in our research, that we can now use this as a tool for clinical diagnosis. But this is only a hope, and has grown to a bit of a dream of mine. I hope this is a role I would like to take, and most likely it's going to totally fail. But it's what's driving me maybe for the next couple of years to see whether we can get this going or not.
Okay, thank you very much. I think this kind of discussions I would like to have again because I think they are very important. Next year we'll talk more about this, in addition to all the cutting EEG stuff that we do. So cutting edge methods for EEG research. Once again, what we like is to bring together the communities that create the methods and those who use it. I personally am from the cognitive background, from a cognitive background, and I'm really happy that guys like you are now talking to me and that I can talk to you. I'm grateful of that. Thank you again for your your time and your insights. I think we're gonna now close this session and the general meeting. No, we're not ready, are we? Yes, we're ready. Okay. So thank you very much, the three of you, and we'll see you all very soon. In the meantime, while I wait for the things that are ready yes, we are here. Okay. Hello. This is the team who organized this event for you. I'll have now some closing remarks ready here. Okay, it took us 3 years to organize this, including hacking a brain hack in Donostia. Hi, Donostia. Many online meetings. Some of them running in my street, trying to catch up with time. But thanks to this amazing set of gardeners that you are all part of, we've finally did it, right? A few numbers about this meeting. We have about 500 people registered on Crowdcast, many of them who actually attended live, more than 700 Cutting EEG members. Thank you all for coming with us on board, and more than 800 attendees across gardens. Therefore, we reached more than 1,000 people today with this meeting. Thank you so much. This is great. During these 4 days, we took 4 COVID tests, all negative, don't worry. Eat 20 grams of paracetamol, 2 tubes of vitamin C, and drank about 8 liters of coffee and about triple that amount of other types of beverages. We slept far less than we should have, obviously. There were more than 250 questions asked in the forum, or not in the forum, but in the Q&A And some of these have been addressed, but not all because of time constraints, right? We are right now asking all the speakers if they have time to answer them in the forum, and we will push them their answers online. So be patient. Your questions all will have been answered. Okay, it was definitely worth the pain, right? So this preparation was no pain, actually, a lot of fun. We are so happy to see how everyone has fostered their garden their own way. Really, we couldn't have hoped better. We have right now a little video to show you. We'll do that in a moment. First, I mean, I need to say a few more words, right? I'm reading, right? Thanks again to the CRNL for welcoming the global team so well. Thanks to Hervé, big up to Complex Cafarnaum for organizing this. Yeah. Thanks. We sent you all paper seeds, seeds in papers right in this, and and we would love it if you would plant them in your garden and send us pictures of them when they are ripe. Now that we have planted the first seeds, this local and global community is going to grow more, and we really hope to see it flourish soon. Thank you all, and bye-bye.
Bye.
Ciao. One.
Where I come from, see me them a dancing now. Corbin now. Dancing now. Dancing now. See me dancing now. Dancing now. To the left, dancing now. To the right, dancing now.
All right, ladies and gentlemen, this is Cutting EG in 2023. We're heading off of Cutting Gardens in Lyon in our bus. We'll see you next time.
Voilà, et on y va bien gentiment, quoi, tu vois. On est en partage, y a rien là.
Good morning, Cutting. Where are we going? We're going to Cutting.
Dancing up, dancing up, dancing up, ah yeah yeah, dancing up, dancing up, dance, ah yeah yeah, aqua ba 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 ba, ah yeah yeah, aqua ba 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 ba. See me dancing now, see me dancing now, see me dancing now, aqua see me dancing, dance. On your feet, on your metal, on your bitty on your metal, on your feet, on your metal, on your bitty on your metal. The money no day to shy you dance, but the day to borrow dance. If you like my disco dance, if you want see tomorrow dance. I dey move, I dey dance, then they look, then they pass. If I bust spots, they go run. If I play music, then go dance. I dey move, I dey dance, then they vex, give me chance. Then blow whistle, then go hide. If I play music, then go dance. Yeah, dance, 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 dance. Ay ay ay, aqua ba 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 ba. Ay ay ay, aqua ba 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 ba. See me dancing now, see me dancing now, see me dancing now. Aqua vena, see me dancing, dance, dance. Ay ay ay, aqua ba, ay ay ay. See me dancing, dance, dance. See me dancing, dance, dance. Ay ay ay.
One of the smallest gardens, working in the smallest plants, drinking utensils. What?
Dancing now, dancing now, see me dancing now, dancing now, to the left, dancing now, to the right, dancing now, see my money dancing now, yeah, dance, 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 ay ay ay, aqua ba 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 ba, ay ay ay, aqua ba 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 ba, see me dancing now, see me dancing.
Hey, this is the beautiful garden of Talca, Chile. We're surrounded by beautiful trees and plants. Hey, Viva
These flowers present this magic garden. We have a lot of seeds and we planted them.
Deep processing.
Developmentally G methods.
Source of construction. MEEG.
I'm Vladimir,
And I am Aygün.
and we're at the Welcome Center for Human Learning
in London.
Hello, this is the bonus garden of CuttingGardens 2023 conference.
I dey move, I dey dance, then they look, then they pass. If I bust spots, they go wrong. If I play music, then go dance. I dey move, I dey dance, then they vex.
Hello, this is Havana Garden over here. Thank you very much for inviting us to this multi-hub scientific meeting. Thank you to the MEEG Association and to the organizers for inviting us.
See me dancing now, see me dancing now, see me dancing now.